Okay, we're back once more. So we know about the planets, we know about how, at least our solar system, how we think it formed. So now it is time to talk about kind of what's left over after the formation of the sun and the planets. So let's remember the final phase of planetary formation, clearing. So material has been flung around a little chaotically. Some of it leaves the solar system through jets as it flies in towards the sun and maybe gets kicked out in a jet-like manner. Others stay within the gravitational influence of the sun, just in a different place from where it started. Like we think possibly these outer large planets could kick smaller objects out into what we'd call the Oort cloud. So, what am I talking about when I talk about leftovers, right? That's what I called the topic of this slideshow. So, I'm talking about asteroids, moons, or planetary satellites and comets. So one of these reservoirs of leftovers is the asteroid belt. So the asteroid belt is found in the region between Mars and Jupiter. So right here, pretty close to the inner solar system. It's about 2.8 AU from the sun. Remember, an AU is the average distance from the Earth to the sun. So it's about 3 times the distance of the Earth to the sun. So this is made up of rocky and metallic bodies with weak surface gravity. So this means that they're oddly shaped, right? Like the planets are mostly kind of spherical. These asteroids are not necessarily so. They're really non-uniform. So these objects show evidence that they went through heavy collisions in the past. Many of them are very, very cratered. And it's possible actually that the asteroid belt is really a disrupted planet. Like a planet kind of tried to form there, but the tug of gravity, especially from Jupiter, it kind of wouldn't let that happen. So we end up having many different smaller kind of rocky bodies. So there are three main types of asteroid. Um, There are asteroids made of silicates. These are stony or S-type asteroids. So silicates or rocks that include silicon and oxygen. These are extremely common on Earth. About 90% of Earth's crust is made of silicates. These types of asteroids also have some iron and nickel. Um, and they make up kind of the majority of the asteroids on the closer edge of the asteroid belt. Next, there's a really kind of broad type of asteroid called a metallic asteroid or an M-type asteroid. These are composed of mostly nickel and iron. So planetary scientists think that at least some of these asteroids have likely melted in the past, which caused heavy iron to sink to the center and for lighter rock to come to the surface. These are really kind of cool objects because they're hypothesized that at least some of these M-type asteroids could have been the cores of rocky planets that ultimately didn't form. The same could be true for these stony type asteroids. Like that could have been kind of the crust. We know it's made of very common stuff that the Earth is made of. Um, so these could be basically the crust and the core of these disrupted planets. So these asteroids could give us some insight into the kind of the core of our own planet, which we can't get to, even though it's right under our feet. So the S and the M type asteroids, they kind of mostly live kind of in the inner part of the asteroid belt, the part of the asteroid belt that's closer to the sun. But there's another type of asteroid called C-type asteroids, C for carbonaceous asteroids. So these asteroids are mostly made up of carbon with some clay and other rocks and are really black. These asteroids, a little different from S and M type because they really kind of need cooler environments to form. So these asteroids kind of segregate themselves a little bit in the asteroid belt, um, in the outer edges of the asteroid belt. So like maybe to 3.5 times further, like 3.5 AU, so 3.5 times the Earth Sun distance. You get 80% of the asteroids there are C-type, right? So the outer edge, kind of the closer edge to Jupiter, has about 80% C-type asteroids. And um, the closer in you get to the sun, that percentage goes down to about 40%. You get way more S and M type asteroids in the closer edge of the asteroid belt. So asteroids are really interesting to study because they are these leftovers from the beginning of the solar system. They can kind of give us a clue of what it was actually like 4.5 billion years ago. But they also aid our understanding in how life developed. So there's one pretty interesting asteroid. I think they found it in the 1960s, 69, I think. It's the Murchison meteorite. It's a C-type asteroid. Um, and it was found to contain in its interior amino acids and evidence that water altered the material. And because it was found inside the asteroid, we're pretty sure that it wasn't kind of picked up when it landed on Earth. So this implies that planets like Earth could have been seeded with water and amino acids from asteroids. The extent to which this happened is unclear, but it's being studied, and this is probably one of the most studied asteroids slash meteorites there are. So asteroids are also really important to track and monitor, actually for planetary defense. When we talk about planetary defense, we're talking about monitoring near-Earth asteroids and more broadly near-Earth objects. It could be comets, it could be asteroids. Um, these can be called NEOs. So these are asteroids and comets that come within 30 million miles of Earth's orbit. So thousands of meteors fall to Earth every year, but the vast, vast majority of them burn up in the atmosphere and don't cause any damage. So large objects that can cause damage are much rarer. 100 years could go by without a major impact. And as of right now, there's no known asteroid larger than 140 meters that has a significant chance of impacting Earth in the next century. But you may have heard of an asteroid recently. This was asteroid 2024 YR4 that we thought for a time had a non-trivial chance of actually hitting Earth in the next 10 years and actually causing significant damage. It was called a city killer. It turns out, though, after careful monitoring, we now think the chances of it hitting Earth are very, very small, really too small to worry about. There's an entire planetary defense office whose job it is to monitor these near-Earth objects and track these kinds of threats. So it's actually really important to keep track of asteroids and comets and these smaller bodies in space. Okay, so the next reservoir of solar system leftovers are planetary satellites, right? Moons. So let's start by talking about Earth's moon. So Earth's moon is a little different from other moons in the solar system. So we think that the moon was formed by a giant impact by a Mars-sized object. So this is called the giant impact hypothesis. And the impactor, the Mars-sized impactor, is often called Theia. So this huge object slams into really a proto-Earth. Earth's crust and impactor material mix together, and the debris eventually coalesces to form the moon. So this hypothesis broadly works out and makes sense, but there are a lot of details about it that we're really still trying to figure out. But the kind of the broad picture of a large impact causing the moon seems to be correct. Other moons, though, show just a huge variety of compositions, like chemical makeup, physical conditions, like they're hot and cold, and orbital properties like inclination or whether they're in a prograde or retrograde orbit. So just take the Galilean moons of Jupiter as an example. So there are four Galilean moons. So Io is the one it's volcanically active. It's one of the most volcanically active worlds in the solar system, with hundreds of volcanoes, some of which erupt lava dozens of miles high. Uh, Io is kind of the innermost Galilean moon and has not only volcanoes, but mountains taller than Mount Everest. And instead of ice, Io is actually mostly composed of rock with a molten iron or iron sulfide core. But Jupiter's largest moon, right, is Ganymede. It's the largest natural satellite in the solar system. It's larger than Mercury. Ganymede's composed, unlike some, of rock and water ice, and 200 kilometers below the surface is believed to be a saltwater ocean. Ganymede also has a really ancient and complex geography with darkened cratered regions and lighter regions that contain an array of grooves and ridges. Callisto is the second largest of Jupiter's moons. It's the third largest in the solar system. Um, this is one of the most heavily cratered natural satellites that we have in the solar system. Um, there is a feature called Valhalla that is a basin over 1,800 miles wide. Callisto also is thought to have a deep subsurface ocean of liquid water. And the last Galilean moon is Europa. Europa is the second closest moon to Jupiter. It's a little bit smaller than Earth's moon, but it has a very smooth and young-looking icy surface, which leads scientists to believe that there's actually a vast ocean underneath all of that ice. And the water stays liquid because of like some tidal heating from Jupiter. It kind of like Jupiter's gravity kind of pulls and tugs on the moon to keep the interior warm. So all of these moons are really kind of vastly different, and um, they're also vastly different from other moons in the solar system. So Mercury's moons, Phobos and Deimos, are thought to actually be captured asteroids. Neptune's moon, Triton, has a retrograde orbit, so it orbits in the opposite direction of the planet's rotation. So that indicates that that was also a captured object, but kind of like a different type than the ones um, that Mars has captured. So the implication of all of these differences is that moons originate from different parts of the disk and arrive at their destination in different ways, right? There's no one way to make a moon. The final reservoir we will talk about is comets. So these are icy planetesimals in the outer solar system that kind of occasionally travel inward. So there are really two spots we find comets. We find them in the Kuiper belt. So right here, about 30 to 55 AU from the sun. So this is where Pluto and other ice dwarf planets live. Comets that live in the Kuiper belt are thought to have formed what we call in situ, or that is, they formed basically where they are now. Right? Kuiper belt objects probably have always kind of been Kuiper belt objects. The second location of comets in the solar system is called the Oort cloud. So the Kuiper belt is kind of like a donut-shaped ring around the solar system. The Oort cloud is more of like a shell, like a spherical shell, um, and that goes from about 1,000 AU to at least 100,000 AU. So the Oort cloud is super interesting. We know it's there because of the trajectory of comets' orbits that come in from that far away. And remember, these were the objects that were flung to the very far limits of the solar system by giant planets during that clearing phase. So Kuiper belt comets, we think, kind of always lived in this area. Oort cloud objects, we think, were kind of flung out there by the kind of the outer massive planets. Okay, so comets, whether they're from the Oort cloud or the Kuiper belt, are basically just chunks of rock and ice and dust. They're often called dirty snowballs. But it's when they get close to the sun that they kind of get their distinctive look. Like really, it's hard to mistake a comet. So as the comet gets closer to the sun, right, it starts to heat up, and eventually the ice begins to turn directly into a gas, right? It goes through sublimation. So this can also cause kind of jets of gas to burst out of the comet, bringing dust with it. So the gas and dust create a huge fuzzy cloud around the nucleus called the coma. So the nucleus of a comet is it's that dirty snowball, right? It's that ice and it's rock and it's dust. The coma, kind of like a fuzzy cloud that kind of erupts around it when things start to sublimate, that is kind of that it's that gas and that dust that's kind of breaking free from the nucleus. So the heating up also leads to the formation of the comet's tail, except when you look closely, comets actually have two tails, a dust tail and an ion tail. So once you see it, you can tell these two tails are distinct. So the dust tail traces a broad and gently curving path behind the comet. So this is the dust tail right here. It corresponds to this in the image. The the dust tail follows the orbital trajectory. So dust just reflects light, right? The ion tail or the gas tail, this is bluish and made up of electrically charged gas molecules or ions. The ion tail always points directly away from the sun. So it's more affected by solar wind. So it comes out of the comet's head, like the nucleus and the coma, at a slightly different angle that corresponds to the solar wind. So that is why these two tails kind of have different angles coming. Like this follows the comet's trajectory, the ion tail follows it's really follows kind of the solar winds. So if we were to map out how the two tails would look on a comet's orbit around the sun, we'd get something like this. The ion tail, which is the dark gray line, always points directly away from the sun, while the gas tail kind of curves with the orbit. So sometimes you can even see a feature called an anti-tail, which is something you can kind of see in this image here. Like right here, we have the nucleus. This is kind of the regular tail, and then we have an anti-tail right here. So what is this thing? All right, so the anti-tail consists of larger dust particles left behind by the comet. So these dust particles are less affected by the sun's radiation pressure and tend to remain roughly in the comet's orbital plane and eventually form a disk along the comet's orbit due to the ejection speed of the particles from the comet's surface. So as Earth passes through the comet's orbital plane, the disk is seen kind of side on, right? It appears as a characteristic spike pointing in the opposite direction as the tail. This makes it look like the comet has a tail coming out front, but this is actually just like a disk of debris, basically, that's coming from the comet. Okay, so this is an image of Comet 103P Hartley. And you can actually see, I like this one, you can see all of the outgassing, right? So this right here is the nucleus, right? And it's outgassing here and creating its own coma and tail. So the chemical composition of comets has been found to be similar to ices in dark clouds and in protostars and protoplanetary disks, making them a really great resource to study if we want to know about the conditions in the early solar system. One of the last things I'll talk about with regards to comets and for this lecture today are meteor showers. So meteor showers are the direct result of comet outgassing and kind of sloughing off material as they get close to the sun. So comets shed material and leave a dusty path in space. So we on Earth get a meteor shower when the Earth's orbit goes through this dusty tail or dusty trail. Those tiny particles then burn up in the Earth's atmosphere and create streaks of light across the sky. The streaks appear from a radiant point, and meteor showers are named after their radiant. So, for example, the Orionid meteor shower that happens in the winter, it radiates from around the constellation Orion. So the name of the meteor shower indicates kind of where to look in the sky. If you were to watch the Perseids, you would want to look towards the constellation Perseus. So you'll often hear about meteor shower peaks. So this is when the number of meteors is expected to be at its highest, but it's possible to see meteor showers for several days or even weeks before or after its peak. Okay, so that is it for solar system leftovers. Shoot me an email or come by my office if you have any questions.